I'm going to start this question by just drawing a diagram and explaining what's going on. It's not absolutely essential to do this, but I just want to give a bit of insight. So what we have here is a position vector. That means like any point along it is described by a vector coming from the origin to the point. Now, as time increases, x is always going to increase. It's always going to be going to the right in the positive I direction, or positive x direction rather. And it's going to be accelerating because as t increases, it's like a cubic in t, so it's just going to go faster and faster. In the y direction, we've got a quadratic term, and it's going to start at the origin for sure, and then there's gonna be a root for the quadratic at 0 and 4/5, which means it's gonna kind of be like one of these, and it's actually going to be going down to start with, and then it's gonna end up coming back up. And remember, it's accelerating in the x direction all the time, so and it's also going to end up accelerating in the positive y direction. So maybe it looks a little bit like this, and then here I am at some time t with my position vector. Which brings me on to part A. So I cannot use the position vector to help me investigate the bearing because the bearing is like the angle that it's moving at a specific time, and the position vector just tells us um, relative to the origin. So what we have to do is investigate the speed, or the velocity rather, v, and that is going to be dr by dt. Remember, these are all changing with respect to time. This is a variable acceleration question working with two-dimensional vectors. So differentiate, I'm going to get 6t squared I, and then over here, next I'm going to get 10t minus 4j. And I want to know what's happening when t is 0.7. So I can just substitute in 6 times 0.7 squared gives 2.94. And then put 0.7 in here. I'm going to get 7 minus 4. I'm going to get 3. So that is going to be my velocity vector. And what that is doing is essentially telling me the direction of motion at a particular point. So here I am, like instantaneously going along this direction, for example. So if I want the bearing, I need to put north in, and north is going to be in line with the y-axis, by definition. And then we want this angle here. So I can turn it into a little triangle. I'm going 2.94 to the right in that instant per meters per second, and then 3 up. So for the angle, it's going to be, I could work out what this angle is. Let me call it x, and then I can do 90 minus that. So x is going to be inverse tan of 3 over 2.94. Which is 45.57. 90 minus that, 44.42, which is approximately 0.44. Remember, three figures, and we're just rounding it to the nearest whole number. Next, we're asked to find the magnitude of the resultant force acting on the particle when t is 0.7. So for this, we're going to need to use F equals ma. But F and A are technically vectors. We just want the magnitude. So put the modulus sign around it or just write F. Okay, but I need A. Now A is going to be the second derivative of the displacement or the first derivative of the velocity. So dv by dt, which is going to give 12ti plus 10j. And when t equals 0.7, a is going to be 12 times 0.7. 12 times 7 is 84, so it's going to be 8.4 I, and then we've still got the plus 10j. So I can do a similar sort of thing here. I can write down that f is going to be, it's 0.12 times 8.4 I plus 10j. I'm gonna multiply through. Should find the magnitude of the acceleration and times that by m. That would also work, but I don't know. I think I prefer doing it this way. So 1.008 plus 1.2 j. Sorry, I've not quite left enough room. I'm trying to fit it all in onto one screen. And therefore the magnitude, right, I'm going to sort of come up here. We can then apply Pythagoras' theorem again. 1.008 squared plus 1.2 squared square rooted. One 1.5671 or 1.57 newtons. Okay, I hope this is making sense so far. We've got the position vector. I've just drawn roughly the path that it's following. I've argued that we need to look at the velocity to investigate the bearing. So differentiated, found the velocity at time equals 0.7, drawn it on to see that this is the angle, because that helps, because actually the bearing is then 90 minus that. It's quite important. You could you could have drawn the triangle differently, to be fair, and then found this angle, I suppose. But either way, the bearing is going to be 44 degrees. Then for the acceleration, we use F equals ma. Work out a by differentiating again. Work out F by multiplying by 0.12, and then we find the magnitude. Finally, we're asked to determine the times at which the particle is moving on a bearing of 45 degrees. So here's my particle. I'm going to put north in again. And we want it to momentarily be going in this direction with a 45-degree angle here. What that means is if I draw the vector out, then this is also 45 degrees. Remember, this is 90, which means this is 45 degrees, and we have constructed, it might not look like it, but it's not drawn to scale, it's an isosceles triangle. And that means the x and y components of the velocity will be equal. So my pen's going a bit slow here. Okay. Now remember we found these before in terms of time. So here it is. 6t squared must equal 10t minus 4. I can rearrange this and divide by 2. So I'm going to get 3t squared minus 5t plus 2 equals 0. Let's see if it factorizes. To be fair, probably a bit safer and quicker to just use the quadratic formula plus on your calculator. I'll show you that in a second. Now, we've got a negative here and a positive here, so they've got to both be positive. So I'm going to have to put 1 here and a 2 here, and then make them both negative. T is going to equal 2/3 or 1. Let me just show you. So hopefully you know this button already, but just in case, if you go to menu, not sorry, I've done that wrong. If you go to not setup menu, and then down all the way to equation function, polynomial 2, we can just type it in 3 minus 5. Quite often you don't get nice answers, and it's, in a mechanics paper, they're not expecting you to show all like full reasoning like this. So we get 1 and we get 2/3 that way. Now, there's actually one thing I've not done. I've equated the components equal to one another, but they would have been equal to one another if we had a bearing of 315 degrees. They would have both been negative in that case. So we just need to justify it. And I actually skipped this. I didn't do this bit when I did the questions. So I think, yeah, I think the mark scheme would have marked me down 1 mark. So basically, because the I component is always positive, then it's clearly going to be a 45-degree bearing rather than a 315. But you have to say words along that line, along those lines. Right. Now this is a little bit harsh because it doesn't say like justify your answer. I suppose you could argue we should always justify our answers. So there we have it. There were actually 2 times when it's going 45 degrees. My sketch is not quite showing it, but one at 2/3 and then one slightly after would give us this bearing of 45 degrees.